Пока можно пригласить всех на защиту докладчик, который будет в пятницу в 4 часа или 16:45 в ближайшую пятницу на заседании ученого совета в 14:08.
Да. Ну, я могу пока просто дать I can give a puzzle. So compute construct a circuit for majority of 5 bits consisting only of majorities of 3 bits, for example. While we're waiting, Semyon. Or explain implicitly why does such a circuit exists.
I think we can randomly choose majority of majority.
So take majority of majorities.
Yes.
So
Of which inputs? So we need now to specify inputs to the bottom majorities.
Randomly.
No, so we have a big tree like this, and then we randomly connect each leaf to something.
yeah, so possibly we can have more than depth 2 here, just very large depth. But maybe somebody can explain
So
or how to avoid probabilistic construction.
So, no, for small n, probably one can try something and just check that it's correct. Or you mean that there is some construction, some other construction which is not the randomization or manual or automatic of this one?
Is it clear that random choice in some large circuit gives us the circuit for majority?
Some argument is needed, definitely.
So what did you say again? Say it again.
As I understand, you suggest to use some large circuit of this type and then randomly assign variables to leaves. And as I understand your claim, you say that with positive probability, the result is circuit.
You can also look at this problem from the other point of view. So we have 5 bits, and we want to find the median, or if you sort, so the goal is to sort this array and find the median of this array.
I see.
And you can do the following thing: you can choose 3 bits. Yeah.
Вы же не начали.
Нет, это было просто в качестве было дано упражнение для слушателей. Но теперь можно начать.
Возникал.
So we will be interested in circuit complexity of majority function. So we will always assume that there is a odd number of input bits, 2n plus 1, and such a function, as you all know, outputs 1 if there are at least n plus 1 bits which are equal to 1, and 0 if there are at most n bits which are equal to 1. So, and I'll probably give some brief survey what is known about complexity of this function, but actually you can even find this in some books on mathematical logic. all these results that I will mention in this survey. For example, in the book of Vereshchagin and Shein, all this is mentioned, strangely. So, like, suppose that we're just interested in the size of the circle. Then, when you want a polynomial size circuit, then this is obvious why we have a polynomial size circuit for this thing.
Non-monotone.
Or, okay, so non-monotone is obvious, yes, so because this function is just polynomial time computed. Well, if you want a polynomial size monotone circuit for this function, well, this is just like an exercise. But the things become interesting when we start to care about the depth of the circuit. So, well, what we know is that, so if you are care about not only size but also depth, and you are allowed to use non-monotone circuits, then the situation is simple, then there exists explicit, well, we can only say that all of log n depth circuit consisting of n ors and negations
And linear size?
I'm not sure about linear size, but definitely size is polynomial since depth is logarithm.
Yeah,
I think the size is linear.
Or probably the
So
size.
you can just add all things.
Yeah, so the idea is that we can find the sum of n integers given in binary by a log n circuit. So yeah, so I always assume that
Саш, можно вас попросить не дальше говорить так же громко, а не тише, как говорили вначале, ладно?
yeah, okay, so
Или даже громче.
so I always assume that we have bounded funding gates. So okay, so this thing is simple, but if you want the circuit with the same characteristics, but in which negations are not allowed, the situation is a little bit more difficult. So there are basically two constructions. One is due to Vэлиент, and he gives all of them depth circuit, let's say so I'll explain what I mean. Majority free circuit for majority 2 to the 1 to n plus 1 bits. So what I mean here, that circuit is allowed to use only majority free gates, so n variables, and
And constants?
no constants. No constants are allowed, and this is important actually. for the rest of the talk. But okay, so definitely if you have such a circuit, then you have the circuit the same depth, just a monotone, standard monotone circuit with ends and ors, because each such gate you can compute by constant depth, constant size function circuit consisting of end and ors.
And what is the size?
The size is, the best known is n something like that. Actually, it is also important.
The circuits.
Okay.
This is for formulas.
This is for formulas, but well,
For circuits, I think the size is smaller. We can do some.
So how much edges, how much nodes we need on each layer to make this work? Just
how much layers?
no, you need logarithmic number of layers.
Yeah.
And on each layers, how many nodes you have?
Well,
About that.
well, I mean, so
Yeah.
the construction is like we discussed.
Okay, no, you also can sometimes, okay, in this way
I just want to tell you
yeah.
how this circuit look like. So we just take a ternary tree consisting of majority free gates. Of some depth, namely depth will be just logarithmic. Okay? So what we can do next is that, and then what we do to the majority free gates on the bottom, we just, for each majority gate, we independently, uniformly at random choose a variable and feed this variable into this gate. Yeah, so, and then we show that with high probability, the corresponding circuit computes the majority function.
No, what I meant that you can have at each layer you have several nodes,
Yeah.
and then you connect a node on the layer to randomly chosen 3 nodes on the layer below.
Yeah.
It's just maybe it could make some improvement in terms of
Yes,
size.
yes, you can do it. You can do it. There is a paper that testing hours.
No, I think this gives no improvement.
Sorry.
No, I think this gives no improvement.
Well, for the size, if you have a circuit and if you study the size,
Okay.
then you can do it better.
And how many you can?
I don't remember.
Because we can, if we are talking about circuits, we can do n cubed log n.
So it's interesting whether they have do something worse or
Okay,
not.
I will check.
Okay, so let me check. So, okay, and this is for formulas. This is size for formulas, and for circuits, I don't know exactly what is current best known. Okay, so the problem with that construction is that this.
I think they have it for n and for I will check. Sorry.
Okay, so the problem with that construction is that it's not explicit. Yeah, so there's no deterministic polynomial time algorithm which produces given n in time polynomial n such circuit. Yeah, so and the question, can we construct a monotone or in particular such a circuit for majority function explicit one? Yeah, so and in some sense this can be derandomized, this construction, so it's a classical construction of Einstein, Cumulus, and okay, so Similarity, yeah. So what they do, they construct now. So what they do, they construct a circuit which sorts the input. So if the input of the circuit are n bits x1, xn, then the output are these bits but in sorted order. x1 prime, x2 prime, xn prime. And the only gate which is allowed in the circuit is a comparator gate. So any such gate just takes 2 bits on input and outputs them in sorted order. So it means that the first output is maximum of bits and the second one is minimum.
Just end and or. Nothing.
Huh? Sorry?
Just end and or.
Okay, yeah.
You can consider sorting for arbitrary elements, but for us it's just.
Yeah. For us, and so if you have such a circuit, you can definitely simulate each comparator gate as you explained by AND and OR, by ANDs and OR, and to output the majority, you just take x. So if here is last x2 n plus 1, so you just take the bit in the middle. And this circuit is O of log n depth, and its size is O of n log n, I guess. And it's explicit.
Explicit in terms you don't need some explicit expander for this, or you have for this parameter you have something.
I guess we have.
You don't need something which is better than explicit expanders. No, sometimes.
Well, I guess people say that this circuit is explicit. There's polynomial time algorithm. So I guess they use expanders which are known.
Yes.
And by the way, it was one of the first papers that used expanders, and it's rather technically complicated. Maybe since then some people can improve things and prove something easier for that, or no.
I guess there are some works which are simpler, but they. So here the problem is to sort the given array.
Yeah.
And some I have seen some paper which explain how, for example, do a merge sort. So in such a way that you do all of log n comparisons per element. But this seems that and there are no expanders there. So basically,
that gives log n squared then for sorting.
So
If you have log n depth for merge,
yeah.
then you get log n squared, log square n depth for sorting.
No, if each element, so the depth of the circuit corresponds to the number of times each element is
no, but merge sort,
compared with someone.
merge sort requires log n layers of merging.
Yeah.
If each layer of merging requires log n.
No, not each. I mean log n.
In total.
In total.
Okay.
But it seems that this algorithm, or at least I don't know, that does not transform into just a circuit. So it's
okay.
but I'm not sure. Okay, so and what we want, so in some sense this is a derandomization of this thing, yeah. But note that here, so assume that you want this circuit for majority, which consists only of majority free gates and variables, no constants. So this circuit doesn't help, but actually we will show that this circuit does help. So so our result that we can take, so we transform this circuit into one consisting only of majority free gates, computing majority. with
So your main result is that you combine the ideas from these two things
yeah.
and take the best from both worlds. You compute majority using only majorities, but in the style of AKS and get
What are parameters of the resulting circuit?
Sorry?
Right. What are the parameters, depth and size of the resulting circuit if you transform?
Okay, so let
this
me
one?
say, so just here, if you state it roughly, without, so we just, there exists explicit of log n depth, majority free circuit for majority 2n plus 1. So
of size and
so you can make it to be of size n squared larger than the AKA's circuit. So you can
cubed logarithm
n cubed log n.
size.
Yeah. And also, we actually show something which can possibly be interesting for lower bounds for majority circuit. So, namely, we show that well, it can be shown that if you have a size S, just as monotone circuit for majority, then there is a S n to the power of logarithm of 3, binary logarithm of 3 size. Oh no, so here we have formula size for majority free circuit for majority. So what does this theorem mean? If you have just any circuit size S, formula, okay? Formula for majority, just standard monotone formula for majority, then we have S multiplied by N, so this is roughly N 1.6 size formula for majority consisting only of majorities.
and if you encode 0 and 1 by vectors with few ones and vectors with a lot of ones, you get something in this direction also.
What? Yeah, I
So
don't-
imagine we have a formula for conjunction or disjunction.
yeah.
Imagine we want to represent conjunction, each binary variable as a vector, and 0 will be vectors with small number of ones, and ones will be vector with large number of ones. Like 10% of ones and 90% of ones. Maybe you can implement conjunction and disjunction by making some majority of some part, no?
I just don't understand.
Okay.
You mean the other transfer?
No. I thought there is some way to perform this transformation and want to say
Okay,
whether
so let's just skip this thing.
okay. It's safe.
So just not to waste,
Yeah.
not to waste time. Okay, so I can start explaining this here. Okay. Yeah. So first step of the proof is, well, let me just start with the following simple lemma. So just what we need, so we need to compute majority from majority free gates. So what we actually do, so the level is as follows. If C is a majority free circuit, and assume that for all x, well, with n ones in it. So if the Hamming weight of x is n, then assume that for every x the following holds. If the Hamming weight of x, or the number of x ones in x is n, then c of x equals 0. Yeah? Okay. This is so all this implies that C computes majority.
Because if weight n plus 1 is just, it should produce 1.
Yeah.
But this is exactly dual thing to this, yeah?
Sorry? You're explaining the proof.
No, it can't be true. You see, assume that the circuit always outputs 1.
But it's made of only of majority 3.
Ah.
So it's self-dual. So if we replace all zeros by 1 in the input, we get the same output. So if we have n plus 1 ones,
Okay.
then C is 1.
Mhm.
So it computes this.
Okay. So should I repeat the proof or everything is clear?
Okay, just say it again probably. Or say something, if you have some other proof, you can say some other proof, it's even funny.
Yeah, so
So-
some other proof will be more funny because it will be more related to the following. So what we want, so why is this true? So we need firstly to show that if the number of x is less than n, then the output of the circuit is also 0. But this is obvious
From monotonicity.
from monotonicity. And how to show that if the number of ones is greater than n, then the output of the circuit is 1. So we can say the other argument. So namely, I want to say that every function computed by such circuit, majority free circuit, satisfies a certain property, which I will call Q2 property.
Wow. And which is different from self-duality.
Yeah. So this property is as follows. So we say that the function f satisfies this property if for any 2 0 inputs, if for all x and y such that f of x equals f of y equals 0, there exists a common coordinate in which they are both 0. Okay? So this is the definition of this property
So it's a property of a function, not of a circuit.
of a function. Yeah.
Yeah.
So and why every function computed by the majority free circuit satisfies this property. So
Very strange property.
maybe okay, I can start and someone can finish. So we can take any two x and y such that circuit output 0. Yeah? And we need to find some coordinate in which they are both x and y are 0. Okay, so what I do? I know that the output gate is 0 for both x and y. So we can descend to a variable. So what we can do? Then we notice that since the output on x is 0, then for x on x, among these three,
Two inputs are zeros.
at least two inputs are zeros. And the same for y. Hence we can find the common gate in which, once again, the output of the circuit, both on x and y, is 0. In this way we can reach some variable which will be 0 for both x and y. And we are done. Okay? So now
There is another proof. So if this is the case, then just consider where x is 0.
yeah. So
And
what
if it's not
are
if
you
it's-
explaining now? Tell us
It's-
this.
Just there is another, I think, more direct proof of this.
That any
Pure two properties.
Of the Q property, property for circuits.
yeah.
So imagine the Q property is not true. Then we have 2x and y, and where x is 0, the y is 1.
Yeah.
So if f was has few zeros and the function was 0, then for self-duality reasons, on y it should be 1.
Sasha,
Not allowed to be so.
no, but Sasha's explanation is different because the circuits he's considering are contained in several classes in postulates. There is one class of self-dual functions, but Sasha is explaining that it's also contained in Q2 class. This is also a class in postulates that is closed under superposition that Sasha just
But since something is which is in majority circuits, it's always self-dual. So maybe it's important class which we need for other reasons, but just from
no, but you are more or less just switching to your previous explanation.
Yeah.
I'm saying that the previous explanation is also proves this level.
Yeah, because circuits are at the same time self-dual.
So actually, it's just so this
Yeah.
this proof just was a good reason to introduce this property.
Okay.
Okay. So
Anyway.
how to prove the level?
Okay, so assume that for some x with more than n ones, it outputs 1. Then some x. You can take y, which is the complement of x. You know. So assume that for some such x with much big
N plus 1.
n plus 1 ones,
It
the output is 0.
Uh-huh.
Then you take also the complement to x, which has at most n ones, and the output of the circuit is also 0. Then we obtain a contradiction with Q2 property.
And why the output is 0?
Because we already have shown that for any x with at most n ones, the output is 0. Okay.
And we obtain a contradiction with Q2 property.
Yeah. So so what we have to do is that we only have to if we're constructing majority-free circuits, we should only care about such inputs. Okay. So now the first step of the proof is to give a reformulation of a task of computing majority by majority free gates. Namely, I will formulate some game between, it's kind of a game in which one player wants to guess something about the input of the other player. So the goal is to formulate a game such that majority 2n plus 1 has d depth majority free circuit if and only if, let's say, So there will be two players, Alice and Bob, so Bob can win in D clashes in the game. Okay, so I haven't defined the game yet, but I am just explaining what we will be going through.
So do you mean that you have the same as Karchmer and Wickerson have for monotone circuit? You have a similar criterion for
It's not a
majority
complication
free.
game, actually. It's not.
Okay, but this is true just for majority of 2n plus 1, or just any Boolean function
No.
has the depth majority free circuits if it will leave corresponding game.
I guess you can formulate something for any function with Q2 property, monotone probably.
But not for arbitrary.
Not for
function.
arbitrary.
Okay.
Because not arbitrary Boolean function can be computed by majority free gates. So for any
Okay, but also it should have Q2 property
Yeah.
if it's computed, and also there should be another criterion inside.
yeah,
this
so we can
computing.
actually show that it's majority free can compute everything from this maybe monotone, well, because it's
Yeah.
monotone.
Mhm.
Okay, but let us understand that at least for majority on 2n plus 1 bits. Okay, so what is the game? Let me call it, I don't know, maybe 2 out of 3 game. Well, as I said, there will be one player which will have some input. Let me say that the input of Alice is x, which is a subset of, so our universe is of size 2n plus 1, and x is a subset of size n. Yeah? And the goal of Bob is to find any coordinate which does not belong to x. Okay? But what is allowed? What Bob is allowed to do in this game? So he can ask a question of the following form. Well, formally what he does, at each turn he makes 3 hypotheses about x. So formally, like what does it mean? So he said he just chooses 3 families from consisting of this subset. Yeah. So and what is each hypothesis is like?
So
No, I understand the notation. This thing it's the set to
X is
answer.
a set.
Yeah.
Sasha, there is confusion before.
Yeah.
X is not a subset.
Yeah.
X is an element.
Yeah.
So X is a set. The cardinality of X is n.
Yeah.
And each 1, 2, and 3 are subsets.
Yeah. So basically, Bob makes 3 hypotheses about x. Binary hypotheses. Yeah. So
Yeah, arbitrary ones. They are not
Yeah.
related to each other.
yeah. So they look like. At first, he claims that x belongs to h1. So he says that something is true for x. This is the first hypothesis, namely that x belongs to h1, then that x belongs to h2, and x belongs to H3. Okay, so assume that we made these three hypotheses. Two of them should be true.
So Bob can start with a very large set.
Yeah, so he can choose any sets. But two of these hypotheses should be true. Namely, if at most one hypothesis, at least two. Namely, if at most one is true, then Alice says that, well, I will not play with you
So
any
Bob
further.
loses immediately.
Bob loses immediately. Okay?
And if there are two, Alice chooses one that is true if it
This
says
is
two.
true. That's
Yeah, and
H1
Alice-
is true.
Alice, well, how to? Alice
Chooses a true hypothesis.
chooses a true hypothesis. Well, if there is three, he can choose one out of three.
So if
Yeah, chooses one.
she
true
always has some choice because at least two of them are true. So it might be that all the three are true. Then
Yeah.
she has even more.
Yeah.
freedom
So, for
to
example,
choose.
she says that it's true that x belongs to H1. Then we also know that some other hypothesis is also true, but we don't know which one. But we only know that this one is true. Okay. So, so why this game is equivalent for?
But wait. So the goal of Bob is to find any J. So does he have a promise that there is such a J?
Of course, because the size of x is
Sure.
n.
The size of X is small.
Yeah. So maybe it is instructive to start why Bob even can win in such a game.
I guess that he starts with sets of large size, say 99%.
Yeah.
We can divide. So at least he can lower and decrease
You
the
mean
set
you
of possible x's.
you mean you want to decrease the set of possible x's by some constant factor?
Yeah, so Bob actually can find this exactly.
How you will do this? For
Okay.
example.
Remove
Assume
three.
that in the beginning all x's are possible. So this is the set of all this is.
Okay. Take three particular x's, different particular x's.
Yeah.
Remove one of them, it will be H1. Remove the second one, that will be H2.
Yeah.
And so on.
So-
That's
So okay. So the first hypothesis is that x is not
different
this.
from that.
That. The second is that it's different from that, and the third one is that it is
Yes.
different from that.
Yes.
Then we can at least two are true because x can be just equal to at least just one of these
Yeah.
three. And Alice says that okay, indeed x is not equal to this.
Okay, then the universe loses one element, and then we can recurse.
Yeah. And but what happens when we are left just with two sets?
So we have now two sets.
Yeah.
Two sets. They have n elements.
Yeah.
And in total, they cover 2 times the elements.
Yeah.
So we can find one which is outside.
Yeah. So, well, this strategy, how many questions this strategy needs?
2n, exactly.
Well, I mean, at each time you remove one x, and there are exponentially many of them.
Exponentially.
But you can, without much work, you can improve it to linear number of questions. So namely, you can decrease the number of possible x's consistent with the current answers by a constant factor by just one question. Well,
So you can divide in 3 parts,
yeah.
equal parts, and then say that
Two of them
H1
fall.
is 2 of them, H2 is the other 2, and H3
Yeah. So we say that x is not here, the second hypothesis x is not here, and the third one x is not here. Two of them are true, so we each time we decrease by like 3
By a
thirds.
factor of 2/3.
Yeah. Okay. So now let me explain the equivalence possibly. Yeah. So
But that's not enough, because
we want logarithmic.
logarithmic.
Yeah, we want logarithmic. Yeah. So I will explain after proving this, I will explain how to win in a game in logarithmic number of questions. Okay? So, but first let us explain the equivalence. So, assume that you have a circuit, majority free circuit. Majority. How can you use to win in a game?
Probably you should say 3 sets corresponding to each of these two vertices or these two vertices.
So
The
this
first
is
level.
down to this 0, right?
Yeah, we assume that so our x is of this size, so the output of circuit on
we know
this,
that output is 0.
yeah, on Alice's x is 0. Means that, well,
At least
There is-
2 of 3 are zeros.
yeah, this means if we just, say that the value of x here is 0, the value of x here is 0, and the value of x here is 0, the two of these will be true. Yeah? And Alice then says, well, some gate, some child of this node on which the value of x is 0. And we descend just until we reach the variable, yeah? While keeping the invariant that on the current node, the value of a circuit on x is 0. On the current gate, the value on x is 0. And when we reach some variable, we know that this variable should be 0 on x. Yeah?
So we input subsets by Boolean vectors
Yeah.
unusual.
You just usual thing. Now, well, the other direction. It's not it's not difficult also, but what should we do? So suppose that Bob has a strategy winning in the game in D questions. So we can draw a ternary tree corresponding to this strategy, and just we will show that this tree. Okay, mainly, well, how you draw this tree? Well, at the beginning, Bob asks some questions. No matter, so he makes some hypotheses, makes 3 hypotheses. And Alice can say that the first one is true, the second one is true, and the third one is true. And then you draw, for each of these nodes, you draw a subtree. Well, the next questions of Bob can depend on what Alice said in the first, for the first question. So we represent it by our tree of the game, ternary tree. Yeah? And in the end, well, we should say that for example, j is not in x, yeah? So in the leaves of our tree, there are some numbers from 1 to n, yeah? Okay, so we have such strategy how to transform it into a circuit. Well, we just do the following. We just replace each internal node by just majority free gate. And each leaf, if the leaf is labeled by j, we replace it by variable xj. Okay? And this works.
So let's verify.
Okay, let's verify. So remember,
So
recall the
we
lemma.
need
Yeah,
to
Is-
consider the axis of Hamming weight
yeah,
n plus 1, right?
yeah.
Or not n, n plus 1.
N.
N
We
or
have
n
to
plus
show that for inputs of Hamming weight n, the output of the gate is 0.
0.
Yeah, because
But we also should prove that for the rest of inputs, the output.
recall the
No.
lemma we have proved.
Only for n.
Recall the lemma that we have at least 2 or 3 proofs. We had at least 2 or 3 proofs in the beginning.
So only on inputs of weight n, the circuit should be correct.
Yeah. So
If
if
it is
it's correct on inputs of Hamming weight n, then it automatically correct on all other inputs. For majority free gates, this is true for circuits with majority free gates. Because of self duality or something else. So there are.
Because what?
There was a long discussion. First of all, Sasha explained my duality arguments. Then another Sasha explained
Self duality.
two arguments.
Yeah.
And then even
So it's true for these circuits with self-dual gate.
Yeah.
okay, let's verify for Hamming weight n.
So what we will let us prove by induction on the depth the following claim that okay, so here we have a node B, and also we obtained with this construction we obtain some function f sub v computed by resulting circuit in this gate, yeah, and we just have to verify that for every x of Hamming weight n, if x is consistent with v, then f sub v of x is 0. Okay, so
is consistent.
what means consistent? So x, it's either you can, it's binary vector, or alternatively this is a subset of size n. What I mean that v is consistent with x. It means that if Alice in the game she receives x on input, it is possible for her to reach the node v. So she can make the corresponding answers. Okay?
Observing the rules of the game.
Yeah.
Assume that this is already shown.
Yeah. So then for a root, what we have? That every
Everything
x
is
is
consistent.
consistent with the root. Then for every x with Hamming n, the output is 0. Okay. Next, let's start with leaves. Yeah. So in the leaf, the function computed by leaf is just xj, if j is the label of the leaf. But if x is of Hamming weight n and is consistent with v, where v is a leaf, then we recall that we are.
Then that hypothesis is true. I mean, the hypothesis that xj0
Yeah.
is true.
Because we output j is the answer to our game, and j should be something which is not an x. Yeah. So this is true for leaves. Now, if okay, now assume that we have proved this for. So let's consider some leaf v, and it has some children v1, v2, v3, and we prove this claim for v1, v2, v3. So why this true for v? So we have some x which is consistent with v, yeah? Then it should be consistent with at least 2 of these nodes, yeah? Why? Because what happens when Alice reaches v on x? Then Bob asks some question, he makes 3 one is true or the second one is true. This means that for each x, at least two. So from this, Alice can go, for example, either to V1 or to V3. Yeah. So both nodes are consistent with x. But okay, recall what we did during this transformation. We replaced this node by majority free gate. Yeah.
So we know that on that x, both functions in V1 and V3 are 0,
Yeah.
and then majority is
On
also
this three bits is also clear. Okay.
No, it's a kind of same strange thing which is in Kashmir-Victorson, and there is a reason why you can believe that this proof is correct. Because if you convert the game to the formula, the game as a complicated thing, strategy, you should decide which questions to ask.
Yeah.
And in this tree, all the information is lost, and the only thing which you use is just the structure of the tree.
Well,
And
we should not forget about the out.
I know the answer. Yeah.
The answers.
So it looks like it's just a version that you invented for Kashmir-Victorson game for majority, and maybe even you can invent something for arbitrary monotone function. So just what is imagine there is some building block which is monotone. Do you have something like this game for this? So maybe you should guess what of the.
I don't have something in mind right now, actually, but maybe we should.
No, but this game, it's you who invented this. It's not something known.
I guess yes. It was not known. But how we did invent it? We just looked at the proof why. So why majority can be computed by majority free case. So recall the question in the beginning, why majority 5 can be computed by majority 3. So there is some explicit, not probabilistic, explicit proof that, well, you should do something. Then we just thought about this proof. And
No, the motivation would be different. So the Kashmir-Victorson game is also very natural when you know it, and it was used for something. But when now it's a kind of a structural understanding of something. So if you achieve the same for majority, for computing Boolean function by majority gates, it's remarkable. But what's that? So you need to do this for not for just majority function of 2n plus 1 argument, but for something more general. And maybe even the building's block can be more. Do you mean that if you have not majority 3 but majority of 5, it won't work?
Majority of 5 can be computed by majority 3 in constant.
No, but there is a question. The function can be computed by a circuit of depth d of majority 5s if and only if something gains something. Probably
I guess, we actually have a generalization of all of these on threshold functions. So on all threshold functions.
But not arbitrary monotonic functions.
I guess.
Gates should be arbitrary monotonic functions.
No, you just have some
You
monotonic.
cannot compute any monotonic function by such a gate.
No. Imagine you have some built-in, instead of majority, you have some fixed monotone function, some other
fixed.
And then you want to find out what is the depth of some function that can be computed by these blocks, by these gates. And maybe there is a result of the same type, which is true for any building block, the circuit of depth.
Yeah, you can.
Is equivalent to some game, but the game should be reformulated somehow.
You probably should have not. Okay, suppose you have a function of k, and then you have k subsets, and
Maybe in those k subsets you have some min disjunction max. It's not majority. If it's not majority.
Yeah, I'm explaining the case. So suppose you have some function, some fixed function, of k variables.
Yeah.
Then in the game you probably will have Bob to ask to give k subsets, such that now the promise is complicated. I think So for each x, we should consider subsets that are satisfied.
And the function of this should be
They
true.
should correspond to me.
I guess so. We just the promise that the value of f is 0, and we want to find the coordinate which is 0. Yeah.
So actually there is probably some game for the big function and for the small function, and somehow we need the reduction to the big to the small, or something. So what I'm saying that to make the miracle less miraculous or even more miraculous, if you prefer, you should state a general statement, and then probably it will be more understandable what is there, what is really happening.
It should be first. We should verify the general statement.
Yeah, that's it.
Yeah, that's what I'm asking to do.
Yeah. Okay. But okay. But anyway, I can explain. I can't now verify whether it's true. I can explain the rest of the proof.
Yeah. So you can explain next time. There's no reason to hurry. Why not?
Okay. So.
And so now you explain it in terms of the game.
Yeah, so I will now explain how to win in the game. Now, actually, let me just explain what we will be using. Some common procedure of the which we will be using in a proof. So assume that we have some function g from the set of all possible inputs or values. Well, do some set W, some finite set W. So I'm claiming that in all of log W questions, you can find two elements of W such that so the value such that the value of x is either W1 or W2. Okay?
Sorry. What is the goal of this game?
The goal of the whole game or this procedure?
It's not a game.
Naive people like us expect that you will now explain how you explain that you need to construct a winning strategy for Bob in some game.
Yeah.
And we thought that you will now explain this strategy. And instead you do something else, so we are confused. What are you doing?
I'm explaining that
Completely different thing.
no. I'm explaining that some general thing which will be used in
Okay.
I don't know. Just for example, okay. So let me explain. So what I want to say that in log n questions, so our goal is to find one coordinate in which x is 0. Yeah.
Yeah.
I want to explain why we can find two coordinates such that one of them is 0 in log n questions.
And then so it's a weaker
Yeah.
goal. But first you explain how can you reach this weaker goal.
Yeah.
But still, the game is the same. So
The goal is different.
we find. I mean, again, we have to produce three hypotheses
Yeah.
so that
And
one
two of them
should be true
Yeah.
and so on. But the goal is different.
Yeah. So and to achieve this, I want to formulate a general lemma what Bob can do.
You have the right to do this, even if it's undesirable.
Namely, assume that Bob wants to learn something about x. Yeah? Namely, he wants to know the value of some function g of x. Okay?
No, but it's natural. So we have some game. So we know the rules, and Bob for some reason wants to do something strange. He wants to find a coordinate where x is 0.
Yeah.
But why should we consider exactly this task? Let's consider more general tasks. He wants to find something, some knowledge on x,
Yeah.
some function.
Yeah. So we
Yeah.
know we want for some function g, we want to know the value of, of x on g. For example, what function we can take? Let's take the following function as an example. G of x equals minimum I such that xi equals 0. Okay, for example, such function. So,
Okay.
well, if you know the value of such function, then we are done. Yeah.
Okay. No, you have the right to consider whatever you want, but you should not overuse this, right? And now we are lost a bit. What?
No, but the strategy, Sasha's strategy is more or less the following. So we want to achieve, to solve some task. We want to find the bits in x such that it is 0.
Yeah.
But we cannot do it in one step. We cannot explain the whole construction in one step.
Yeah.
So he will make a small step right now. He will find 2 coordinates, of which one, at least one, will be 0.
And the strategy in this weaker game doesn't correspond to any claim about circuits. It's just a strategy.
Yeah, now we are just talking.
Yeah, yeah. So, and I will use the same thing, just I will use the same thing several times. And I want to formulate this explicitly. Yeah?
Okay.
So Sasha is devising some tool that he will use.
Yeah. So I'm dividing. So my tool is that if I want to know the value of x, the value of some function on the input of x, I can find not one but 2 possible values of g in that many questions. So at the beginning, you know that, for example, the value there are for some function g there are n possible values. So after log m questions, you can reduce this to 2 possible values.
Yeah.
How? So you can. So now I will explain how to reduce from m to 2.
By covering the possible values by 3.
Yeah.
by 3
So I
points.
have 3 possible values, or some set of possible values. I divide them into 3 parts, and I make the hypothesis that the value is not here, the value is not here, and the value is not here.
Yeah.
One of them is verified, so we remove one part,
Yeah.
and we reduce the number by a constant factor until we are left with just 2 possible values of g. So, in particular, if we apply these to this function, just which takes x and outputs the minimum, the leftmost coordinate in which x is 0. Yeah.
Yeah. So, but this construction somehow is working for every function.
For every function. Yeah.
Without any. So you don't need g to be simple or a circuit to have a circuit. Just
Yeah.
for any function g.
Yeah.
Okay.
So, okay. So now, so after that,
You have 2 values of
yeah,
possible.
let's say these are I and J.
Yeah.
So, and I want to apply this thing the second time. Namely, I want to know what is the value of xi xj. Okay? So I know 2 possible answers, y and j.
Yeah.
Okay, so now let me ask.
Wait, you know that it is 0.
I know that one of them is 0.
So
But
it's
The
xi
product is
xj.
0.
It's
The
a
product
product or what? Of the pair.
It's a pair or a product?
It's a pair.
Ah, pair.
So it is either some AB or CD. Okay?
Yeah.
Well, this just costs, I don't know, a constant number of questions
Okay.
because there are 2
So you
possible
know that
values.
either
The form.
A or C.
No, there are, in this case, we have 3 possibilities. Because
Ah, yeah, so
First
one is impossible. So we can just make one question for this. So why not?
Yeah.
Okay.
So you exclude some combination.
So this was some pre-processing. Now, I have said that we will use the
Sorting
AKA circuit
For so
in our construction. But actually we just need not a sorting circuit, but just we take any explicit, you can take any explicit log depth monotone circuit for majority. Well, and it will be more convenient to transform, to consider the corresponding monotone Kashmir-Wigderson game. Yeah? So we now suppose we have some monotone circuit for majority. Explicit. Recall what the Kashmir-Wigderson game is. So now it's a communication complexity problem. So in this problem, Alice gets some x such that majority of x equals 0, and Bob gets some y. Well, maybe let's not confuse it with our other with the previous notation. So Alice gets some vector u on 2n+1 bits, such majority of u is 0, and Bob gets some u such that majority of bit is 1. And the goal is to find some coordinate. The goal is to find some, let's say, k, such that u k equals 0 and vk equals 1.
So we have some strategy, unknown strategy,
Explicit
explicit strategy for
Yeah.
doing this.
Yeah.
And
So, and it's even simple. It's easy to explain how you to transform this from a circuit to.
oh yeah.
But I don't know. Should I repeat this? How we do?
And I hope we don't have time for that.
Okay. But there's not a lot left. No, okay. Next, let us. So, what is this game actually? Kashmir-Wigderson game. So, here Alice has some u such that the size of u is most n. Yeah. Well,
Yeah.
and here the size of v is at least n+1.
Yeah.
So assume that.
So they should find something in the difference.
Yeah. So assume now that Bob inverses each of his bits. What the problem what now the problem looks like if Bob reverses each of his bits? Now the input of Alice is of size at most n, so there are at most n ones, and the input to Bob is of size at most n.
And you need to find something in the complement.
Yeah.
Yeah.
Okay. So now we assume that we have a protocol, communication protocol for this problem.
Yeah.
How to transform it into the strategy? So, well, so you know there is a protocol, and in some nodes, Alice communicates, sends one bit, in other nodes, Bob sends one bit. So what we will do, we will descend from the root to a leaf. Yeah? And we will keep some invariant. Let me try to formulate this invariant. Namely,
But won't we use this A, B, and C, D?
we will use it. We will use it. This was a preprocessing, some preprocessing. Okay, so let me try to formulate the invariant. So at each moment of time, we will have some current node, u. Yeah? And in this node,
Not you, double U.
okay, double. But anyway, so some current node. And in this node, well, recall rectangles and everything like all this stuff. So there is, for each node, it has an associated rectangle. Yeah? Namely, L is the set of all inputs of Alice which can come here, and R is the set of all Bob's inputs which can come here. Yeah?
Okay, just say something, because we are lost completely, but when you just continue, maybe at some point,
Yeah.
because we are just where we are, but okay.
The problem is that we made some preprocessing already. We do not use it at all, and then consider something completely different.
It's like, like in modern music. Sometimes I don't know, the fine instruments start playing something very loudly, and then they stop immediately, and some other things.
No, but if you think about the processing stage, you just know that there are two cases. Either xij is ED or it's CD.
Yeah.
So,
that's all we know.
either x is in L and xi xj, and what are xi xj?
These are two variants of each
A and B,
A and B.
are the beats or what?
beats.
Beats.
So xi and xj are beats.
And what is x?
And
X is the input of
you are
Alice.
using this function, so A, B, C, D should be zeros.
No, we know that one of them is
One of them
is zero.
is zero. Yeah. Okay.
So the invariant is either x is in L or in R. In
Yeah.
R.
No, the invariant is either x is in L and xi xj equals AB, or x is in R and xi xj
So the
equals
weaker
zero.
invariant is just that x is in the union of our L and R, right? It's a weaker invariant.
Yeah, it's a weaker invariant. Yeah, and we have stronger invariant. But okay, so let's why in the beginning the invariant is true? In the beginning, the node is a root. So hence
Here and
the
R are
rectangle-
the whole space. So
the rectangle is just the whole space. I don't know. So well, we already know that xi xj is either AB or CD, and this in the root, these are all just the whole space. So at the beginning, the invariant is true.
Okay, assume that in the leaf the invariant is still true.
Yeah.
And what?
And then, well, so now in the leaf we only use the fact that x is either in A or in R. It means that if Alice has x on input in the protocol, then she can come to the leaf, to this leaf, and in this leaf leaves the answer to the problem. And the answer to the problem in this problem, so there are two vectors with small number of ones, and we want to find the common zero.
Yeah.
It means that, well, if x can come to this leaf, then the label, so if the answer here is some t, then xt should be zero.
So if we come to a leaf, keeping the invariant, we have found the type,
Yeah.
which is
Because just either x is in A or in R. But in any case,
in any case.
or
Xi
one
is
of the
zero.
players in the communication protocol can come to a leaf with having x on input, and hence the answer in the leaf will be the correct answer.
So we don't need the second part of
Yeah,
the
we
invariant.
need it to make
Make
a
a
step,
step.
to maintain the invariant. Okay, so let's just make the step. So what
A, B, C, D are the same for the whole.
for the whole
They are fixed.
movie? Okay, so we want to descend B by one. Okay. So, for example, let's look at this situation. In this situation, Bob makes a move. Bob sends the bit. So there is some function phi which tells, well, depending on what Bob has on input, whether he
So
sends
we
0 or
want to
1.
choose one of the
Yeah.
children, right?
Yeah. And we make the following three hypotheses. The first one is that it's not true that xi xj equals ab and f of x. No, what? Yes, the first one is that it's not true that xi xj equals ab. The second one is that it's not true that xi xj equals cd and f of x equals 0. And the
What
third
is 5?
phi is the function of Bob. Well, this is a function from the communication protocol in the corresponding node. This function determines which
determines the sum.
Five is 0
if Bob sends 0
Uh-huh.
in this node on his input and 1 in the other. So, and the second is the third hypothesis is like this: ij equals cd or f of x
Or
f of x equals 1. Okay. So why
at least 2?
why these two are true? Because if you just forget about negations, you see that these three possibilities are disjoint, yeah?
No, they're not. All the 3 possibilities are disjoint. Right?
Yeah.
Uh-huh.
Because, we assume that A, B, and C, D are different, because if they are equal, we already know the answer. And so all the cases are replaced into three disjoint groups, and you say that the first one that this is not true, the second one that this is not true, and the third one that this is not true. Okay? So the two of them are true. And then Alice says, okay, so one of them is true. So for example, assume that it says that this is true. Then we are done already. Do you see why?
Because we know that xi xj is cd.
Yeah, and we know the answer. Now assume that Alice says that something of these two equals is true. For example, this is true. Then what we should do? We just move here. We just move here
To the right.
to the right. Because, informally, because Alice said that this is not true, that f of x is 0. Yeah, so we know that f of x is 1. But let us verify our invariant more accurately, yeah? Because we have here or something like, yeah? Okay. So, there are two cases. So what we need to verify is that this is true. So what here the rectangle looks like?
Wait, if the first option was true, then L is not changed anyway.
Yeah. So here rectangle looks like A times R1, where R1 is just is the subset of R in which F is 1.
So nothing has changed and the first option remains true.
Yeah, so if xi xj equals AB, then we know that x is in A. In this A, then of course this is in the same A. But now, if xi xj equals CD, then, f of x is either 0 or 1. But this possibility is thrown away. And we know that f of x is 1. Then what we obtain is that if xi xj equals cd, then, and we know that then x is in R, okay? And then,
That arc which corresponds
and
to...
then actually, since we know that f of x then is 1, then x is an R1. And
Sasha, do I understand correctly that we can just say here that now, so in B we have two cases here, x is in L and x is in R. And we more or less just break the second case down to two subcases.
yeah,
X is in R1 and x is in R2.
yeah.
And then we ask, in the game, we ask a question, so we make three hypotheses. Either the first two are true, or either the first or the second case, or the second or the third, or the first and the third.
Yeah, yeah.
And then we get transferred.
Yeah.
I think it might be just. It's the same, I think, but it may be better to explain.
Yeah, but this is just the same.
Yeah.
Just literally the same. I guess.
Yeah, I think you will, this way you don't have to hide anything on the board.
Okay, yeah, so do I have time for something else? Not really.
Okay, but it seems that at least you understood something and have some idea what is happening. So maybe you can clean all this to get it some reasonable form and explain what is really happening. Because it's kind of strange in terms of Kashmir-Witgerson translation. So you construct, you somehow start from the difficult side. You don't construct, instead of constructing a circuit, you explain also the strategy. So it's just you need to provide more information, not just the scheme of the protocol, but also the functions in the vertices.
Well, the game in the whole idea is that it is easier to win in a game than construct a circuit.
But to win the game, you need first to construct the circuit and also to provide the strategies and the vertices. But what is you use the same translation in difficult direction for Kashmir-Witgerson.
So Sasha, the game and the circuit is exactly the same. You can transfer it.
You can transform,
The only
but
difference is that you construct the circuit from the bottom usually, and the game you construct from the top.
yeah, but in the game you also need to specify the strategies and the vertices.
But they are they have natural correspondence.
No, they have natural correspondence when you have the tree. So you can say that you have the tree of the game, and then you can reconstruct the strategies by looking in the circuit and back. Okay, this is philosophy, so don't worry.
Yeah, the whole idea was that the games are simpler to understand.
No, something is happening, but Shaggy will explain what is happening probably in the next video.
Вообще, на следующий раз Миш, я предлагал, что помните, я в марте пытался про свои замощения рассказать, но тогда не очень получилось.
Не получилось.
Получилось рассказать, но не уверен, что хоть кто-нибудь что-нибудь понял.
Нет, ну я запомнил, что там ничего написать нельзя, по сути.
Я
не проверил.
Саша не было. Я хочу следующее.
Было, по-моему, убедительно, но это значит, что тебе хочется сказать еще раз.
Да.
Нет, это можно сказать еще раз.
Да. Хорошо, нет, но так как
Нет, тем более тогда я не вполне был уверен, что доказательства везде правда.
Нет, но так я надеялся, что ты здесь произведешь разъяснительный доклад, а ты наоборот запланировал зажигательный. Но в смысле разъяснительный.
Нет, может быть, ваши философские общие тезисы чуть-чуть более высказались, а их надо повторять.
Да, нет, повторили очень хорошо. Но объяснить, что говорит Саша, тоже
Ну, я боюсь, что это
Саша, я не понял. Что именно ты хочешь, чтобы он...
это же это было очищено и в каком-то, так сказать, весь мусор выброшен, и можно было понять, что происходит, сначала до конца нет. Но происходит явно что-то замечательное. То есть, как бы, то ли придуманы новые игры, типа Кашмир-Витgerson в каком-то общем случае, и какое-то вот что-то такое замечательное происходит, тем более, что не думают, что ровный способ
учителя физики пробовал.
Да.
Учил следующее, что
Да.
цель учителя — это как следует запутать ученика, чтобы у него появился...
Нет, я понимаю, ты скажешь, что мы ленивые, вместо того, чтобы самим разобраться в удачно запутанном.
Да,
Саша, в принципе, наверное, какой-то шаг можно было пропустить. Может быть, вот конкретно в этом рассуждении можно было не Игорь Кашмир-Витgerson сейчас посмотреть, а просто брать формулу.
Нет, надо не опустить шаг, а надо наоборот получить.
Формулы, да, но там инвариант сложнее.
Больше контекста
Сформулировать.
Не общается, Саша.
Ну, собственно,
Там
да.
больше
Да.
Нет, надо как-то понять, что происходит, так вот, в каком обществе, что на самом деле верно, и как это разъяснить. Но Верещагин
Но
уклоняется.
это недостижимая цель.
Почему? Надо только его убедить, чтобы он...
Нет, ну давай другой раз.
Хорошо, другой раз.
Не, ну потому что это как бы никогда, это, ну, нету предела, так сказать.